Good afternoon, all. Welcome to the session of computer architecture. So, in this session, we are going to see about performance metrics. The session is presented by myself, R. Narendran, working as assistant professor in Erode Sengodar Engineering College in the Department of Information Technology. In the previous sessions, we have discussed so many basic concepts regarding computer architecture. So in this session, we are going to see about the performance metrics related to how we can um, provide performance related constraints in computer architecture. Okay, with no further delay, we shall move on to the topic. So, what is performance metrics? Basically, not only computer but also to every constraints and every things we will have to find the performance metrics in order to analyze how efficiently it is working. So computer performance is no wonder than the amount of work accomplished by the computer system. So the performance will be carried out and calculated by means of three important things. First one is response time, second one is throughput, and the final one is execution time. There are so many different constraints and sub constraints related to computer architecture performance metrics calculation. So, what is response time? So, the response time is nothing but it is the time from the start of the work and the completion of the work. Can say it as the time duration between start and completion of a particular task. Okay, this also includes operating system overhead, how effectively the operating system is being utilized. So next one is waiting for IO, that is input output devices and its operations, and also other processes. Processes in the sense we can take it as multi-threading concept. Okay, so next one is accessing a particular disk or memory. Okay, that is accessing the peripheral devices and the memory management systems. So the next one is the time spent in executing a particular process on the CPU, or the execution time. Execution time itself is a performance metric constraint. So in that, the response time is also dependent upon the execution time, how long it has taken to execute a particular task. Okay, next one is throughput. Throughput is the total amount of work done in a particular period of time. Suppose the computer has been assigned a particular task of copying a particular file from one particular location to another particular location. So in that particular sense, the throughput is nothing but how much amount it has taken to do that particular copying accomplishment. Okay, so this is called as throughput. So the total time, so the total amount of time a CPU spends in a given period of time. Okay, the total period of work completion is done in how much amount of time. Next one is CPU execution time, is the total time a CPU spends computing on a given particular task. Okay, so it also executes time for input output operations, peripheral devices, and how long it has taken to run some other programs after finishing the currently assigned programs. So okay, you can say simply this as a CPU time, central processing unit execution time. Okay, so how the performance is being calculated? Okay, the performance is determined by execution time, as we have already discussed in the previous slide, right? So it is inversely proportional to the execution time. So for example, performance is equal to 1 divided by execution time, that is the reciprocation of execution time. Similarly, the execution time is the reciprocation of performance, that is execution time is equal to 1 by performance. Okay, so suppose when we are going to compare two different performance, two different computers having different performances, we have to find out the ratio between the performance of a computer A and performance of a computer B. Okay, A and B are computers. So the performance of A divided by performance of B is equal to execution time of B divided by execution time of A, because the performance is inversely proportional to execution time, right? So for example, a machine runs a particular program in 100 seconds. That is, the first machine A runs in 100 seconds. The machine B runs the same program in 125 seconds. So how can you calculate the performance ratio? uh, uh, so the performance ratio, before going into that, the performance ratio is nothing but the calculation of how speed the computer works comparing with the another computer. For example, A and B are the computers we have been taken. So which one is the fastest um, performance related computer, that we have to find out. So for that, we are assigning performance of A divided by performance of B is equal to execution time of B divided by execution time of A. We already know that the A computer runs in 100 seconds. Likewise, the machine B runs in 125 seconds. So 125 divided by 100, we will get 1.25. So that means in the machine A is 1.25 times faster than machine B. Okay, so this is the simplest example for performance calculation. So the performance metrics, the formulations are: execution time is equal to CPU clock cycles into um, clock cycle time. So execution time is equal to clock cycles of CPU divided by clock rate. The number of CPU clock cycles, that is determined by CPU clock is equal to number of instructions executed in a program into number of clock cycles spent in a particular instruction. So we can consolidate here as instruction count into clock cycles per instruction, CPI. Okay, so execution time is equal to instruction count into CPI into clock cycle time. Okay, so that is what we have seen. So the units for CPU execution times are, okay, so CPU time is equal to seconds per program, so our instructions per program into cycles per instruction into seconds per cycle. Okay, how we can improve the performance? The performance can be improved by means of improving the overall efficiency of the computer. That is the first one. So logically speaking, we have to go by decreasing the clock cycles per instruction that is assigned by the hardware. For example, we are using the hardware which is utilizing minimum number of clock cycles for executing a particular instruction, then the performance will be increased, right? So and also decrease the clock time by reduction the propagation delays. So likewise, we can also decrease the number of required cycles or improve the instruction set architecture, ISA. Okay, that's a different topic. We will see in the upcoming classes, ISA. Okay, instruction set architecture. So CPI, we can say yes. So cycles per instruction, right? So clock cycles equal to summation of CPI, clocks per instruction or cycles per instruction, into instruction count. We can substitute from I is equal to 1 to n, because n number of instructions can be executed at a particular period of time, right? So weighted average of CPI is equal to summation of I is equal to 1 to n clock cycles per instruction for n number of instructions into instruction count divided by instruction count. So it's related to relative frequency, how often the instruction is being executed in a particular period of time, that is the relative frequency. Suppose when we are looping a particular instruction for a n number of time, so it is having the highest frequency, right? So finally, um, let us see another example. CPI, for CPI. Okay, so alternative compiled code sequences using instructions in classes A, B, and C. For consider A and B, A, B, and C are the different classes of computers having different clock cycles and instruction sequences. Okay, in the table we can find out a CPI for a class A, B, and C, and the instruction count in sequence 1 for A, B, and C, and instruction count for sequence 2 for A, B, and C computers. So instruction sequence 1 is equal to IC is equal to 5, because we can directly relate to that, and instruction sequence 2 is equal to IC, that is IC is equal to 6. So we can count 2 plus 1 plus 2 and 2 4 plus 1 plus 1, so we can directly get. So likewise the clock cycle of particular first set is 2 into 1 plus 1 into 2 plus 2 into 3, right? So comparing with the different clock cycles, so that likewise we can get the average CPI. So how much clock cycles it has spent divided by total number of IC. So here we have already found out in the first case 10 is the clock cycle, and IC is equal to 5. So 10 divided by 5 we get 2. So average cycles per instruction is 2 in the first case, and in the second case you can see that clock cycle is 9 and IC is equal to 6. So 9 divided by 6 we get 1.5. So average CPI is highest for the first case, and whereas it is lowest for the second case. Okay, by using these constraints we can able to clearly formulate and clearly identify that which particular system is having highest performance. The system having the highest performance only will be more eminent to be utilized for distributed systems or a file sharing systems. Okay, so then only we can process the data in a fastest manner. So in this session we have discussed the various topics related to performance constraints and performance metrics, from which we can calculate the performance of a particular computer for executing a same set of instructions by comparing with the two or three different set of computers. So in the upcoming sessions we will discuss the more topic related to instruction set architecture, and followed by the various topics in computer architecture. Okay, so thank you for listening. We will see in the next session in the upcoming classes. Hope you will like it. Thank you. Thank you for listening.